Nanomaterials and nanostructures exist everywhere in our natural world. Take a look at the wing of a dragonfly. If we zoom in 100,000 times and look at the transparent membrane, we can see the nanostructures, which are invisible to the naked eye. Graphene is transparent. This is a molecular model of graphene. To make it visible, it has been magnified over 280 million times. Graphene consists of only one single element, carbon. It's so simple. However, graphene has lots of special properties. It's the thinnest of all materials, only one atom thick. It's the strongest material ever measured. The in-plane carbon bond is stronger than the tetrahedral carbon bond in a diamond. At the same time, it is flexible and stretchable. We can fully bend graphene and stretch it up to 20%. It has the highest thermal conductivity of all materials, including copper. It can withstand the highest current density at room temperature. It has the highest intrinsic mobility, which is 100 times more than that in silicon. And it is the most impermeable material. Even the smallest helium atoms cannot squeeze through. Graphene will change the world. There will be for sure a completely different intelligent society in 10 to 20 years. Let's spend some time thinking about the future. Imagine if all the transparent glass windows could constantly generate electricity under sunlight and supply the energy for all the buildings. Imagine if all the electrical vehicles and electronic devices could be charged within 10 minutes and last for a few days. Imagine if the seawater could be desalinated with a pocket device so it turns into drinking water everywhere. Imagine if the smart electronic devices could be integrated into our clothes, and some of them even implanted under our skins. Imagine if the lightweight composite material could be stronger than ever, so it turns into the main structure material of the body of ships, vehicles, and airplanes. Imagine if the electronic chips could do computation 1,000 times faster with plasmons instead of electrons. All these dreams will one day become real and revolutionize our society. And I believe it will happen in our lifetime, thanks to the exploration of this new nanomaterial. But how to produce graphene is a serious problem. Although graphene was known to exist in graphite, most scientists believe that it would be impossible to isolate a stable graphene. In the 1930s, Landau and Peirce predicted that 2D crystals would be thermodynamically unstable and thus could not exist. 30 years later, Mermin further presented the analytical result to further validate this hypothesis. Until 2004, when two scientists, Andrew Geim and Konstantin Zholov, used a Scotch tape to produce graphene. By putting tape on graphite flakes multiple times, each time peeling off a layer, the graphite will become thinner and thinner. Although most of the area consists of thin graphite flakes, a few small pieces of single-layer graphene were finally isolated. Since then, thousands of scientists started to do research based on this tiny piece of single-layer graphene using the Scotch tape method. Can you believe that the Nobel Physics Prize in 2010 was awarded to these two scientists based on their groundbreaking Scotch tape experiment? Obviously, it's not a practical way to mass-produce graphene, and make useful product. Nowadays, tons of small flakes of multi-layer graphene, strictly speaking, thin graphite flakes, can be produced using the chemical exfoliation method. It can be mixed into tennis rackets or bicycle tires to enhance the strength and lower the composite weight. However, the material produced is black, which is inconsistent with the transparent property of graphene. If the color is black, it means the flakes are too thick. At the same time, the flakes are too small to do the cool things with that I was talking about. As an experimental researcher working on graphene, I need lots of large area, single-layer graphene for my experiment. However, I couldn't find any research group which could supply me with high-quality graphene in the Netherlands at that moment. I traveled between Leiden University and Delft University every day and tried to figure out how I could grow large-size graphene sample. With the existing facilities available, I couldn't isolate high-quality graphene, either because the equipment had very rough control of the gas flow, or because the heating area was too small to grow larger-size samples of graphene. Even the power of the heater was not sufficient to reach 1,000 degrees Celsius. Day after day, I woke up at 6 a.m. and returned home at midnight. I tried all the possibilities that I could think of. However, what I got was only frustration and reiteration of the problems. I thought, if I continue in this way, I will never finish my PhD research. 4 months later, I decided to stop wasting time and make furnace myself. Thanks to my supervisor and the faculty, I received extra budget for the equipment. At the same time, I also won the Young Wild Idea Prize worth 10,000 euro, which allowed me to spend the money freely on the material. I still remember that moment on Tuesday, April 17, 2012. After a whole year of working long days, I started the first testing of my own setup. The vacuum pump I grabbed from somewhere in the lab was over 8 years old and had run for over 29,000 hours. Not only that, but the pump will stop running once the temperature reached over 40 degrees Celsius. So I bought a small fan costing 30 euro, which did a perfectly good job of cooling the pump. This is the furnace I have built. I will explain the advantages of this homemade setup. The furnace can heat up the 1-inch quartz tube to over 1,000 degrees Celsius with a temperature fluctuation of less than 1 degree Celsius. There is a transparent, bulletproof Lacen cover which can protect against any possible gas explosion and secure the safety of the researcher. There is a small hand wheel which can remotely control the moving of the furnace to the left and right with a gear and chain, similar to chain gears on a bicycle. With this design, I was able to heat the sample and cool the sample 10 times faster than commercial equipment. And the cost of this setup was less than 20,000 euro, which is over 7 times cheaper than any commercial available equipment. All the components can be optimized and well controlled, and it delivers a much better performance. I enjoyed conducting the experiment with my own setup. This is the graphene I have grown. The graphene crystals grow like snow crystals. Methane gas, which accounts for about 80% of natural gas used for cooking, can decompose to carbon atoms on copper substrate at 1000 degrees Celsius in an inert gas environment. The carbon atoms will attach each other and form carbon rings with honeycomb structures, such as in graphite. I can use the carbon isotope to mark the growth procedure. Can you imagine? The size of individual graphene crystals reached over a few millimeters, which is over 1 million times larger than the size of the carbon atom. Can you believe that this sample was made 6 months ago, and the single-layer graphene can still protect the copper against any oxidation? The graphene crystals will grow larger and larger and connect with neighboring graphene crystals to finally form a continuous film. Once there is no bare copper, the graphene growth will stop. So in the end, we will have a single-layer, high-quality graphene film. My colleague and I proved for the first time that the quality of this synthetic graphene is as good as the one with the Scotch tape method. However, the size is considerably larger. To mass produce a graphene and reduce the cost dramatically, a bigger and better furnace was designed and built. The furnace has a larger quartz tube, and the furnace will always maintain a constant temperature. Once the graphene growth has finished, the only thing I need to do is to move the furnace completely away from the tube and take out the graphene sample. Immediately, I can start the second graphene growth cycle. The efficiency of high-quality graphene growth can be improved 10 to 20-fold, and the energy consumption will become much lower. If we build hundreds of bigger furnaces, the mass production of graphene will become possible soon. There is a layer of graphene on a transparent substrate. I can see you all through it. But there is something special. It is conductive and flexible. Now you can imagine all kinds of future applications with this graphene. Currently, the price of this small piece of graphene will cost around 1,000 euro. I believe the price of this graphene will go down to less than 1 euro within a few years, because the material we use to produce graphene, such as natural gas and copper foil, are widely accessible. All of us will have access to graphene in the near future and realize this dream. Remember that I told you we are going to have a better world. Now I cannot show you the transparent glass windows which could generate electricity, and I cannot show you the electronics in my clothes. But I can show you something you have never seen before. There is a transparent graphene patterned into wire structures on this transparent polymer wing. The graphene is so special that once we put a tiny amount of energy, it will shrink. And graphene is so strong that it can lift up this polymer wing, which is 1,000 times heavier, and mimic the flapping function of a biorobot. Look at what I have done and what I have achieved in these few years. With all of you involved in my endeavor to mass produce high-quality, large-scale graphene, I believe we can make our dream come true together. Thank you.